In this example, we're told we have a water tank that has an orifice or a hole at the bottom of it. The area of that hole is A at y is equal to 0. Y is the distance from the hole headed downward. And what we're trying to do is find the height, or the cross-sectional area, sorry, A at any position y. And we're trying to figure out what that area is in terms of A when y is equal to 0, H, which is the height of or the depth of the water in the tank, and y, which is the distance at some arbitrary location below the hole. And we're also told that the height of the water in the tank, this h, is kept constant. We can also neglect viscous effects and surface tension. So there are actually a couple of items that we'll have to make use of to solve this problem. The first is conservation of mass. And specifically, we know that any fluid that comes out of that hole is that same water is going to be the same water that crosses that boundary. So we're going to apply conservation of mass to that control volume. So if I write out conservation of mass, okay, so here's the conservation of mass statement. The first statement is the time rate of change of mass inside this control volume. Well, since this height here is kept constant, it's always going to look the same as a function of time through here. It's never going to look any different. So this is 0 because this is steady. It's not going to be changing with time. The next term will be the mass flux that comes in and out of the control volume. So we have mass coming in here and going out there. So at the inlet, it'll be minus rho, let's call it V sub naught times A sub naught. So V sub naught is this velocity there. I don't know what that is yet. I'm going to have to find that. A sub naught is just this A at 0. And the minus sign comes into play because of this dot product. The velocity is headed down. The unit normal vector for the area n hat is pointed upward. So when I do the dot product, this gives me the negative here. Now let's do the mass flow rate at the exit down in here. Let me call that velocity there v sub y. In the area there, I'll just call it a sub y. So there, we'll have a plus rho v sub y, a sub y. And that one's positive when I do the dot product because the outward pointing normal vector there, n hat, is in the same direction as v sub y. So that's why I get the positive v sub y, a sub y when I do the dot product. All right, so we can go ahead and rewrite that. You see that the rows cancel one another out, and then I'll have v sub y is equal to v sub naught times a sub naught over a sub y. All right, so that's just part of the problem. Obviously, we can't, what we're trying to find is the area a sub y in terms of these other things, so we need something more than that. In order to find these velocities, I know I can also use Bernoulli's equation. Right? We're told that we can neglect viscous effects, and it's a steady problem. So let me apply Bernoulli's equation along a streamline that goes from the free surface out to this point and then on to that point. So we're going to call this, so we're going to do Bernoulli's equation along those points. And let me just put some labels on this. We'll call this point F for free surface. We still have point 0 here for the right where the exit is, and then point Y here. Okay, so we'll apply Bernoulli's equation along that streamline. So we have P over rho G plus V squared over 2G plus Z. I need to put in a coordinate system here. I'll put my coordinate system right there. Actually, you know what? Let me take that back. We have our coordinate system. Coordinate system is right there, so the origin is right there. So when I write out Bernoulli's equation, I'll just use that as my coordinate system. So this will end up being minus y. Okay. And the reason it's minus is because the y direction is in the same direction as z. So if I increase y, then my potential energy gets smaller because I'm headed down. Right? I'm going further down, so my potential energy gets smaller if y gets bigger. So that's why I have a minus y here. And we know that this is a constant along a streamline. So I'll just figure it out. I'll just do it at point F, and then I'll also do it at point 0. Oops, that's a minus y. All right, so let's apply Bernoulli's equation between those 2 points. First of all, at point F, right here at the free surface, I know the pressure there is atmospheric pressure. Let me write this down here. So P at F is equal to atmospheric pressure. I know the velocity at F is 0 because the free surface here isn't moving downward. So the velocity is 0 there. And the elevation of this will be minus h using my coordinate system where y is pointing downward. So y f is equal to minus h. And then over here, on this side, we have p at 0. Well, right at the exit here, this is just the start of a free jet. So the pressure there will be the same as the surrounding atmosphere. So it'll also be p atmosphere. V at 0 is something I don't know yet. I'm going to try to solve for that. And y at 0 is just 0 because that's the origin of my coordinate system. So you'll see that the pressure terms will cancel out because they're the same pressure. We don't have this y naught term. We don't have this vf term over here. And what we'll get when we substitute in is that v naught will come out to be the square root of 2gh. So we now know this expression there. And then now let's find Vy. We can still use Bernoulli's equation from, let's go ahead from point F all the way to point Y here, Vy. So it's still along the same streamline. So if I do it there, what I'm going to do is just dot, dot, dot. This dot, dot, dot just is this term right here. And then that's going to be equal to Bernoulli's equation on the right-hand side. And this is at point Y. So the pressure at point Y is also atmospheric because it's still a free jet. It's still exposed to the atmosphere here. The velocity there, Vy, I'm trying to find. And the elevation there is just y. It's the distance. It's the distance from, the distance from our origin. So again, if we simplify Bernoulli's equation here, what we're going to get is the pressure terms will cancel out. The velocity at point F is still 0. We still have minus h there. What we'll end up getting is v sub y is equal to, this will be the square root of 2g h plus y. So that's what that'll simplify to. So we can take that and substitute it in right up there. And then if we do that and do some rearranging, we can solve for a sub y. So let's do that. So we have on one side, rewrite this. We have square root 2g h plus y. Other side we have the square root of 2g h times a naught over ay. And you'll see the square root of 2g cancels out. We'll get ay is equal to a naught times h over h plus y. And there's a square root there I should be careful of as well. Let me just double check that I've got that all written correctly. Yeah. All right, I think I've done that all correctly. So this is our final result. So the area of that jet as it goes further and further down, you can see it goes sort of inversely with the square root of y. This is actually a simple enough experiment. You could do this at home. You could just go ahead and take your phone, fill a container filled with water, and make sure that the container here is pretty wide, and then have a hole in the bottom of it, and then take a picture of this with your phone, and then you could measure the area, the cross-sectional area here. It'd be like a diameter, since if you made a circular hole. And as long as the container is wide enough here, even though this height will be changing with time, it'll change very, very slowly. So you can still make the assumption that it's a square, it's a steady flow. It'll still be close enough to be a reasonable assumption. But take the picture right away, and then you can go ahead and compare your result to what we predict here and see how that turns out.